Hey guys, we are attempting to solve Fick's laws. So there are primarily two reasons for it. One, as we have considered in our discussion, it has significant relevance to material processing. Even in this case, we are trying to increase the hardness of our metal rim, and in order to do so, we place it in a carbon-rich environment, allow the carbon to flow into our rim. Now this happens primarily because there is a gradient in concentration, and this in turn induces a diffusion, and this diffusion is governed by Fick's law. So wherever diffusion is involved in material processing, which is primarily governed by diffusion, the rate of diffusion or the rate of this processing is dictated by Fick's law. So therefore it's relevant for us in the context of materials research to understand or solve the Fick's law. Now there is another reason purely from the mathematical perspective. Fick's law, or solving it, allows us to get acquainted with two different approaches of solving PDEs. So the first approach we considered in our previous discussion, we call that approach as an analytical approach. So this approach, in this analytical approach, this could of course could have been done using pen and paper. So what we essentially did was, if you consider the whole scheme of things, what we essentially did was we converted our PDE to that of ODE, which we are at least in theory able to handle well. So we converted this PDE to that of an ODE. The way we did it was we introduced a couple of dummy variables. We non-dimensionalized our parameters and introduced a couple of dummy variables. So that allowed us to convert our PDE to that of ODE. And once we had this ODE, using our understanding that we have gained in our previous session, we were able to solve it. We assumed that we would be able to solve it, and ultimately we ended up with an expression like this. So this is what we refer to as the analytical solution. Since we took an analytical route, lo and behold, you have analytical solutions. So what these analytical solutions mean is that when I plug in, or when I substitute, or when I start considering a specific position and plug in that value, and consider a specific time, plug in that value, I will be able to say what is the concentration at that position for a given time t. So when I take my Fick's second law, the PDE, solve it analytically, it gives me an expression. I substitute for my position, I substitute for my time, I end up knowing the concentration at a given position for a given time t. Now this is the analytical approach. Now we are going to consider a completely different paradigm called as a numerical treatment. Now when we say that the computational research or computation is involved in solving this expression, essentially what they mean by that is they are taking a numerical approach to solve the expression before them. The expression before them, a PDE, they solve it using numerical approach, and that is what they mean when they say they use computational technique to solve it. Now, as opposed to analytical approach, wherein we just directly jumped into the problem and we tried to solve it, in case of the numerical treatment, what the foundation of it is, or it depends on the basic definition of each of these terms here. The numerical approach is founded on the basic definition of each of these terms here. So what we mean by that? So when I consider the term to my left, what this term essentially says is how my concentration is changing with respect to time for a given position. So when I fix a position, I want to know how my concentration is changing with respect to time. Imagine that I fix a position in my system and I was able to track my concentration change with respect to my temperature. My change in concentration with respect to temperature, and I'm plotting it. So let's assume that this is how my concentration is changing with respect to my temperature. So if this is known to me, I will be able to find out this left hand side term here. The left term here I will be able to find out. All I need to do is consider a time t and find the corresponding concentration C of t. And I have to consider another time, let's say t plus delta t, and find the corresponding concentration. So this will be concentration at t plus delta t. So when I subtract these two, that is the concentration at different times, and divide this difference in the concentration or concentration at different times with these two time differences, then essentially I will be able to find the change in concentration with respect to my time. So all that I'm doing is considering two different times, or let's say time steps. I'm considering two different time steps, I'm identifying the concentration at these two different time steps. I'm considering the difference between the concentration at the two different time steps as my numerator, and at the denominator, I'm just considering the width of these two different time steps. So when I do that, I'll be able to find out the left-hand side of my expression. So this is fundamentally the definition of the partial derivative of my concentration. So partial derivative of my concentration is when my position is fixed, I just understanding how my concentration is changing with respect to time. So I take two time steps and consider the concentration at these two time steps, take the difference of these concentration and divide it by the width of these time steps. I end up with this expression here. Now it is also possible. So in this case, I considered a time t and a time t plus delta t, which is in the future. So I consider a time t and I consider a time t plus delta t in the future. It is also possible for me to consider a time t minus delta t in the past and correspondingly find how my concentration is changing with respect to time. When I do that, I end up with an expression like this. So there are two ways for me to calculate, provided I know how my concentration is changing with time, if provided I have a plot for it, I know a trend for it. It is possible for me to find out how my concentration is changing with respect to time by either considering a time step in the future with respect to my present or a time step to my past with respect to my present. When I do that, I'll be able to find out how my concentration is changing with respect to time. Now it is vital to note that this and this and this and this, they are equivalent. Again, this is something that we are familiar with, only when my delta t is close to 0. This relation holds true only when my delta t is close to 0. If my delta t is not close to 0, if it has a quantifiable value, then it becomes approximately equal to 0, which means this, the way I'm finding out my partial derivative using this here, kind of deviates from my actual solution. If my delta t is not equal to 0 and it is quantifiable, then my equal to is replaced by an approximate sign. So what it essentially means is, this term, the way I'm finding my partial derivative, it deviates from the actual solution or the actual derivative, the ground truth or the actual derivative. And this deviation is what we refer to as the error. So if I have this expansion and the delta t here is not close to 0, then if I have to use this equal to sign here, then I have to include an error term. So I'm solving my term at the left of my equation. I'm doing it by my fundamental definition of the derivative. I'm considering a time step either in the future or in the past, and I'm considering the concentration at these two different time steps and dividing it by the width of the time step. And depending on the size of the width, either if my width is close to 0, it's extremely close to 0, then this will be equal to my actual derivative. If not, I have to have an error term, which if I'm able to find, I'll be able to include it and then replace my approximate sign with an equal sign. Now this is what we refer to as, since we are considering a time in the future, we refer to this approach as forward difference and this approach as the backward difference for finding the derivative. So in this case, I'm considering a time in the future, so I refer to it as the forward difference, and in this case, I'm considering a time in the past, so I refer to it as the backward difference. Remember, this is possible only when I know the concentration in the future. This is possible when I know the concentration at a given position in the past. All right, so we have forward difference and we have backward difference for solving this term here. Now, apart from forward difference and backward difference, there is also another way of solving it. When I solve this partial derivative, so essentially I end up having an expression for concentration that varies with time. Now this, I can expand it. Assuming that my concentration at time 0 is smooth, meaning it is possible for me to differentiate it, then I can expand this solution for my partial derivative using Taylor series as something like this. Now when I solve this, I find out an expression for the concentration with respect to time, and if I assume that my concentration is differentiable at 0, then I can expand it using Taylor series in this form, wherein this term includes all the terms that are of the order 4 and above. Now instead of the 0 if my expression here is differentiable at say a point A, at time A, then I can expand my function here using Taylor series as this. So when my function is differentiable at 0, the Taylor series expansion would give me something like this. If my function is differentiable at A, then I would get a Taylor series expansion like this. Now, it is also possible for me to express the function t or expand this function t plus delta t using Taylor series expansion in this way, assuming that my concentration t is differentiable at time t. So instead of expanding c of t, I'm now expanding c of t plus delta t, assuming that my concentration is differentiable at t. When I do that, I end up having an expression like this. So I have an expansion, a Taylor series expansion of this form here. The same can be done for t minus delta t. So I have a function t plus delta t and c minus delta t. I'm expanding it through Taylor as a Taylor series. All that I'm assuming is this function, that is c plus delta t and c minus delta t, is differentiable at t. So I have these two expressions, and what I'm interested is in the left hand side of my equation, that is my first derivative of c with respect to t. So I'm interested in finding out this guy, and this guy appears in both these expressions here. So now all I have to do is subtract these two, and I will end up having an expression like this. So this is a Taylor series expansion for t plus delta t. This is a Taylor series expansion for t minus delta t. I just have to subtract these two. Now I have an expression that has c plus delta t, c minus delta t, and the first derivative of c with respect to t plus an additional term here. Now I can rearrange this, and I will end up having an expression like this, which tells me what is the first derivative of my concentration with respect to t, considering my future and the past. So what you essentially have is this term talks about the future of the concentration, this term talks about the past of the concentration. So based on the future and the past, and including the difference in the times between the future and the past, so 2 delta t is nothing but the time difference between the future and the past, I'm able to calculate the first derivative of my concentration. Now I have this term here. Now this is the term that allows this time to be equal, meaning when I take this approach to find out the first derivative of my concentration, this delta t is rather measurable, quantifiable. So it means there is an error associated with it, and this term captures the error. So what I essentially have now done is I have come up with a way of estimating my first derivative of concentration that considers both future and the past and the time difference between these two, and includes also the error that comes up from this approximation. So since there is an error associated with it, we refer to it as the approximation. So I consider forward difference, I consider backward difference. Now we have both forward and backward, so I call this a central difference approach or central difference approximation, because it includes an error term. So depending on the delta t, the error will change, and when I have my delta t rather less than 1, this significantly minimizes or diminishes. So from this expression here, from these two expressions here, I will also be able to estimate the error for forward and backward difference. So this here is forward difference, and this here is backward difference. From these two expansions here, I will be able to calculate the error for forward and backward difference. When I do that, I end up having the expression like this. So this is my forward difference, this is my backward difference, this is my central difference. So as you can see, when my delta t is less than 1, my central difference will give me less amount of error, will be the most accurate one when compared to forward difference and the backward difference, because this quantifies my error. So when this quantifies my error, then when delta t is less than 1, my central difference will give me a more accurate approximation when compared to that of my backward difference or forward difference. So what we now essentially have is we found a way to calculate the first derivative, more than one way, we have 3 ways now, and we found one way that is more accurate than the other. So we refer to that as the central difference approach. Now these expressions here essentially takes care of the left hand side of an expression. These are three different approaches or three different approximation essentially takes care of the left hand side of our expression. Now let us consider the right hand side of our expression. We begin by just replacing our time, that is our variables, that is t and delta t, with x and delta x. So we replace or rewrite this expansion in terms of x and delta x. So we have these two different expansion for forward or for x plus delta x and x minus delta x. Now, since we are focused on the right hand side of our expression, the original Fick's law, it means we are trying to find out the second derivative of concentration with respect to our position. So that means we are interested in these two terms here, this term and this term. So in order to find these two terms, all that we have to do is add these two expansion. So I'm interested in second derivative. So if I want to have an expression for the second derivative, I just have to add these two. When I add these two, I have an expression like this. And when I rearrange this expression, I would ultimately have found out the second derivative. So what this second derivative of my x is? So I'm interested in finding out the second derivative with respect to my position, and that is equal to this expression here. So what this means is, if this is my position x, and I have x plus delta x, and I have x minus delta x, the change, the double derivative of my concentration with respect to my position is how my neighbors are. My double derivative, how my concentration is changing with position is, or the second derivative of my concentration with respect to my position is, this is my neighbor, and this is my neighbor, and this is my actual value divided by the width or the distance between my neighbors. So the way the concentration changes with respect to the second derivative of my concentration with respect to my position, it depends on myself and also my neighbors. So as per the actual definition of the derivative with respect to position, the same is applicable for the second derivative expansion here, meaning the change in concentration, the second derivative of my concentration with respect to a given position depends on my neighbors, and the way it depends on is written in this way here. Now again, this is a central difference scheme, and the error associated with the scheme is expressed here. So I have an expression for the double derivative using central difference, and I have seen the expression. So this is what we have for the right hand side of my expression, and we have already seen three different approaches for the left hand side of my expression. So all I need to do is I need to bring in one of these solutions for my left hand side and one of the solutions for my right hand side. So in case of right hand side, I'll go with central difference because this is the most accurate one. The amount of error is significantly lower or relatively lower, so I will go with the central difference. Now as far as the left hand side of my expression goes, there are three options. One is forward difference, the other is backward difference, the other is central difference. In forward difference, I need to know t plus delta t. In central difference also, I need to know t plus delta t, meaning I need to know my future. So knowing future, unless otherwise you have a crystal ball with you or you are some sort of a psychic or prophet or whatever it is, you will not be able to do so. But in case of backward difference, we need to just know t minus delta t, which is our past. Fortunately or unfortunately, we always remember our past. So even though the future is unknown to us, or since the future is unknown to us, we will not be able to use our forward difference or backward difference, or rather central difference, for the left hand side of our expression. So the only solution that is left for us is the backward difference. So you replace this term here with the backward difference description. And for the right hand side of your expression, you take central difference because central difference gives you the least amount of error, or the deviation from the actual solution is the least in case of central difference. So you go with the central difference for the right hand side of your expression. You choose backward difference for the left because you don't know the future. In case of the right hand side, there is no time involved. All that is involved is the spatial position, so you can go forward and backward. So you can take central difference, meaning you take an approach that gives you the least error. So you can rearrange this term here, you can rearrange these terms here, and you can have an expression like this, which tells the concentration at a given time t depending on the concentration in the previous time step. So now we have an expression that stems from the approach that we have taken that tells us the concentration at a given time t based on its past. So that is what we have here. So basically, the way we are finding out, the way we are solving the Fick's law is, in case of the numerical approach, the way we are solving is by coming up with such an expression which tells, or which rather ascertains the concentration at a given time t by considering its past that comes here and also the neighbors of the position. So when I am finding the concentration at a given time t, I am able to find it by considering my concentration at the past and also the concentration around my position. So the around my position comes from, or this takes care of the second derivative with respect to my position, and this comes from the right hand side of the expression, that is the time derivative. So basically, in numerical approach, I'm trying to find out the concentration at a given position x and a given time t by considering the neighbors of my position and also considering the concentration in the preceding time step. So by combining these two, I'm able to find out the concentration at a given time t. Now when you compare the analytical treatment to that of the numerical approach, in analytical approach you have an expression for concentration. All you have to do is plug in x and t. You will be able to find out a concentration at a given position at a given time t. However, arriving at this expression or arriving at this relation from the PDE is not straightforward. In this case, the arriving at this expression is rather straightforward. All we have to do is expand or do the Taylor series expansion, sum it all up, rearrange the term, you arrive at this. Arriving at this is not much difficult, but you need to know, if you want to find the concentration at a given position, at a given time, you need to know the concentration in the preceding time step. Supposing if I want to know the concentration at time step 1, I need to know the concentration at time 0. That is my initial condition. Of course, in these other cases also the initial conditions are required. So what my concentration at time step 1 is equal to is nothing but the concentration at time step 0, the preceding time step, plus the second derivative, that is the neighbors. It depends on the preceding time step and its neighbors. So the second derivative of concentration, so this term takes care of the neighbors. So the second derivative of concentration with respect to its position, that plus the concentration in the preceding time step will give me the concentration at this time step. So when I iterate it, then I will be able to find the concentration at all time steps and at all positions. So when I have an initial condition, that is x naught and t naught, and from that I'm iterating this particular expression here, I'm calculating, keep on calculating it, then I'll be able to find out my concentration at all time steps and at all positions. So when I want to estimate what is my concentration at a given time t1 and a given position x1, all I have to do is stop iterating at that point. So my numerical approach, essentially it keeps on iterating the expression I have before me. In case of my analytical approach, I have a relation, I just have to plug in my values. The difficulty with analytical solution is to derive it or to arrive at this relation is quite difficult. It's not that straightforward. But in case of numerical approach, the arriving at this relation, the foundation of your numerical treatment, the arriving at this relation is rather straightforward. But when I want to find the concentration at a given time t, I need to know the concentration at the time t minus delta t. So if I want to know the concentration at t minus delta t, I have to go know the concentration at t minus 2 delta t all the way going back to t0. So I do it iteratively. I know the concentration at all the time steps. So when I pinpoint a given time step, I will be able to find out the corresponding concentration. So that is how the numerical approach works, and that is the other technique that we consider is the analytical approach. So these are the key differences. So as far as the approach in itself goes, the numerical treatment is rather relatively straightforward when compared to analytical approach. But as far as the application goes, analytical, once you arrive at the equation, applying that equation is rather straightforward. And so you have this analytical equation, applying it is straightforward. You just have to plug in x and t. But applying the numerical approach needs an iteration. And of course, the accuracy of the solution here depends on the combination of delta x and delta t. You have to be extremely careful because this is the term that governs the error So we have to choose appropriately our delta x and delta t. So basically, there are two approaches to solve the Fick's second law. One is analytical, pen and paper. It gives us a wonderful relation provided we are able to solve it accurately. Plug in those values, you get an answer. In case of numerical approach, you go back to the fundamental definitions and then come up with a rather straightforward relation to solve your PDE. You iterate it. Of course, when we talk about iteration, this is where computers get involved, and that's the reason why we call it as a computational technique. So you reiterate it several times till you reach the point, the time point and the position that you are interested in. So you reiterate it, and then you will be able to come to your solution. So these are the two different approaches, and these are the characteristic or primary differences in these approaches. And when we want to consider the concentration evolution, how the concentration is evolving in a 3-dimensional space and a 2-dimensional space, generally you would go for a numerical approach over the analytical approach, because the way we are approaching the solution is rather straightforward when compared to that of the analytical. So therefore, when the solution is not known, when the analytical relation is not known, you go with the numerical approach, wherein you iteratively solve your expression for different time steps, and correspondingly you find your concentration. So with this, what we have done is we have considered two different ways of approaching a PDE, which governs the spatio-temporal evolution of a variable, in this case concentration. So when you find such an expression, any such variable that is associated with your materials research, you would be able to adopt one of these two different approaches to solve them. So with this, we are done with our discussion on differential equations. We will move on to a totally different topic in the subsequent lecture. Goodbye, guys.